Okay. So look, for example, if we move from here, bottom to top, we have device. Okay, we have circuit, we have gate, module, system. Okay, now each of these different layers are giving different kind of information. Okay, so the system is at the top, that is the most complex thing. And a system consists of many modules. Okay, and one module may consist of many number of gates. One gate will consist of some circuits. Okay, and then a circuit will consist of several devices. Okay, so there is a clear cut connection between each of these layers. Okay, and the purpose of each of these layers are different. Okay, for example, look at this device. We know that what kind of device it should be. Okay, it should be a MOSFET, it should be a kind of transistor. Okay, so most of the time it is going to be a MOSFET. Okay, so if it can be a N MOSFET or P MOSFET. Okay, but basically the device is some kind of field effect transistor. Okay, the device in VLSI is referred to a transistor. It may be a NMOS, it may be a PMOS. Okay, look at here, the source, gate, drain. Okay, we know that the MOSFET has got three terminals, basically a source, a gate terminal, and a drain terminal. And there are, for example, this is a N MOSFET, this is N plus region, this is N plus region for drain, and they will be connected by a gate channel that will form under just gate. Okay, so a device is a transistor, a field effect transistor in VLSI, and this is the most fundamental thing, because all of these upper layers will ultimately be decomposed in terms of some kind of gate. Okay, be it a system, module, gate, or circuit, whatever, ultimately it has to be some kind of device resting there at the bottom which is operating properly. Okay, and then we can use some few number of devices to construct a circuit. Okay, look at here, for example, this is a simple inverter. Okay, and this is PMOS. PMOS means PMOS, P kind of MOSFET, and this one, the bottom one, is N MOSFET. Okay, so basically a circuit will consist of some number of devices connected properly. Okay, so circuit will be a more complex thing as compared to a device, right? Similarly, a gate can be formed by combining different circuits in a proper fashion. Okay, so we can have, let's say, we can have NAND gate. For example, we can have NOR gate. We can have, okay, the handwriting is not good right now. I will start using the slate from next time. Okay, today I forgot to bring it. I'm writing it with the help of mouse. Just an XOR gate. Okay. Okay, now power came in the college. uh, so a gate would consist of several circuits, which in turn consist of some devices. Okay, now when we move one more layer upwards, we have modules. Okay, so we can form some specific modules like adders. We can have adders, multipliers. Okay, we can have multipliers, divider, etc. Okay, which may in turn consist of some gates, because these modules will be made by using these basic gates, right? You know that we know that, for example, a full adder consists of some XOR gates, AND gate, OR gate, okay, those kind of things. So basically a module will be something which will be consisting of some gates, and which will be used for doing some specific functions. Okay, but by and large, if we compare it, or if we think in terms of a system, the module will still be a small block. Okay, and several such modules of different kinds of functionalities will have to be connected to form a complete system. Okay, which would rather satisfy to a certain specification, and it will do a certain kind of job. For example, a chip, okay, a microprocessor chip, a DSP chip, you can visualize those things as a system, complete system. Okay, so now look at these, they are interconnected. Okay, the top layer is made up of the just bottom layer, just beneath layer, and this layer will be made up of some components from just the down beneath layer, and like that. Okay, and each of these layers in themselves are huge, huge in terms of what I mean to say that you'll find engineers working on some particular layer of abstraction. For example, so you'll find engineers or scientists working on just devices. You'll find engineers working on just these layers. You'll find engineers working on these layers. Okay, you'll seldom find engineers who is working on all of these layers, because the work is huge. Okay, most of the time they uh, work for a certain layer of abstraction, and they communicate with the engineer which is working on the other layer. Okay, which is working in the next or next to next layer. So they communicate with each other, and you'll find that to make a complete system, okay, there are different teams. There's a huge there will be a huge team which consists of different small teams, and those small teams are working on different, layers, different kinds of different areas in VLSI, within VLSI. Okay, so you will not find a single person working on all of these things. That is what I mean to say that. Okay, so these devices, for example, these MOSFET will be governed by their device equations. Then we will have the circuit and device circuit equations for these layers. And for designing modules and systems, most of the time we will use some kind of SDL language, for example, Verilog or VSDL language. And by writing the code in VSDL or Verilog, and then verifying those things from architecture. Okay, so those things are done here in the top layer. Okay, and this is just an overview for from this is I'm giving here just from an overview point of view. Okay, uh, when we move to the next slide, we see simplified design flow. Look at here. Okay, this shows a very simplified design flow in VLSI. Okay, which you might have heard about the two kinds of approaches that are uh, present there for designing the things. Okay, it is not restricted to design just VLSI chips, but basically you can apply these things to design the things or machines in any field of engineering. Okay, so top down and bottom up approach. So top down, uh, someone is trying to join, let me check. So we can have these kind of approaches, either top down or bottom up approach to design a chip also. Okay, either we can move from top to bottom or from bottom to top. Okay, now practically most of the time this is not exclusive to just one of these approaches, but you will find that most of the time it will be a combination of top down and bottom up approach both. Okay, certain times it is better to go with top down approach, certain times it is better to go with bottom up approach, and somewhere you combine these two approaches and you get a final product. Okay, now look at here. As we move from top to bottom, we are moving from system to device. Okay, you relate it to the previous slide. Okay, there was device, circuit, then module, then system. Okay, now when we go to the system, the that was at the topmost level. Okay, so we start with the design system specifications here. Specifications are collection of parameters which needs to be satisfied for a particular design. It may be in terms of area required, that this particular chip should not uh, consume this should be consuming only this much area. Okay, it may be in terms of power, so that it does not consume more than the power requirement given by this parameter. Then delay, speed. Okay, it should work with this, at least with this speed, like those things, etc. Okay, so there would be many more constraints like these parameters, which form a system specification. And when you start a design in the starting, okay, you'll have to study these specification, and accordingly you have to start your design, so that you match your design chips performance with these specifications. Unless that thing is not matched, then that product will not be accepted uh, by the client. Okay, then we start with the architectural design, the overview design. Okay, which will may consist of several blocks connected in some fashion. Okay, and then we do the verification of this architecture, whether this architecture is working fine or not. And this, look at here, this verification term is very important because it is appearing here and here and here and here. So the thing is that whenever you design something, okay, you verify it. If it is fine, if it's working properly, we go ahead. Otherwise, we go back to the previous step, and we again do the modifications needed, and then again we go for verification. So okay, suppose you have designed some kind of adder. Suppose you have designed adder. Okay, now designing adder is one thing. You have designed this adder, but are you sure that this adder is working according to the specification, according to the truth table? Okay, is it functioning properly? Uh, to make sure, it needs to be done with the functional verification part. Okay, so what you will do, you will verify this circuit by giving certain inputs. Okay, and you will get certain outputs, and then you will match this output, and then you will match this output, okay, for the corresponding inputs with the truth table. Okay, and if it matches, then you may be sure that okay, this adder is working fine. Okay, so that's a kind of functional verification. Okay, so at each of these design stage, whether it's function architectural design or logic design or circuit design or physical design, at each of these design stages you need to verify that design. Okay, and that is why you find these kind of verifications here. So after functional verification, we go for the logic design or gate level designs. Okay, and then we verify that logic design by logic verification, and then we move to the next down level, that is circuit design. Okay, try to connect it with the previous slide. Okay, and then we go for the circuit verification. Okay, and beyond this, it's the physical design, which is actually related to the device. Okay, so these are related to the device, that is the actual transistors. And the transistors are represented in terms of layout by some layout diagram. Okay, because we know that transistors are basically what they are formed with the help of material, some kind of material, silicon material. Okay, and we have diffusions, n plus, we have layers for gate, we have deposition for metal interconnects, metal linings. Okay, all these things are represented with the help of a layout diagram, geogrammatically. Okay, which shows the actual structure of the device. That is why it's called a layout of physical design. Okay, so these two things are related to the actual devices, and after layout verification we go for the fabrication and testing part. Look at here again, this is not just fabrication, fabrication and testing. Okay, when you fabricate some IC, you need to test it. Without testing, it is not okay. You cannot be sure of your device, of your chip, without a testing part. It has to be tested. Only then the product is launched in the market. Okay. So this is about the simplified VLSI design flow. सर वो फैन वहाँ से ऑन होगा या फिर यहाँ बैठ जाइए सर, हवा लगेगा सर वहाँ से, सर वहाँ. Okay. So after that, uh, 11, after that, looking at simplified VLSI design flow. Again, that same thing can also be related to this Y chart. Okay, this also illustrates the VLSI design flow in the form of a chart. Okay, this was first proposed by a person called as named D. Gazki. So named after him. Also, it's sometimes called as Y chart or Gaussky chart. Okay. Uh, Look at this, resembles to a Y alphabet in English language. Okay. So this Y chart illustrates simplified design flow for most logic chips using design activities on three different domains, which resembles the letter Y. Okay. And what are these different domains? The domains are the structural domain, the behavioral domain, and the geometrical domain. Okay, the structural domain will certainly tell us about the structure. Okay, what is the structure of anything? Means that what kind of components, with what kind of components it is actually consisting of, and what is the structure of those components. Okay, geometrical will talk about the uh, placements of different modules on the given area. For example, if this is a chip area, okay, now on this area, this is the total chip area, okay, and we will have different modules, okay, different sub modules which are doing some functions, and the task will be to arrange those different sub modules within the given area so that the area is utilized in the most efficient manner. Okay, it is the similar task. If I give an example, for example, there is a classroom, and in a classroom there are some number of benches that needs to be adjusted. Okay, now how will you arrange those benches in the classroom so that maximum number of benches can be adjusted and maximum number of students can sit inside the classroom? So this is kind of some similar task. Okay, so that we can adjust more number of modules in a given area. Obviously this will be subject to some terms and conditions. Those conditions has to be satisfied. Okay, now the outer development of hardware is perceived within three domains. Okay, these are the domains. Along these areas are the abstraction levels that describe the degree of abstraction. Okay, so these are the different abstraction levels uh, along these domains. Okay, we will see these things, and the outer ones are the generalizations, and the inner ones are the refinements of the same subject. So as we move from outer to inner part, we move from the more general part, okay, into the more refined part. Okay, it is similar again to that layers of abstraction slide. Try to remember, we had system at the top, and then as we moved downward, we had seen device at the bottom part. Okay, now Gatsky supported that. Gatsky proposed that the design can be done on three different domains. Okay, behavioral domain, structural, and geometrical. Okay, now behavioral domain mostly will consist of such kind of things or conditions which describe the functioning of the system or module or transistors. Okay, so at the most at the most outer level, we have algorithms which are describing the functioning of these chips. Okay, and parallel to this we have processor. Okay, and parallel to this we have chip floor plan in the geometrical domain. Okay, now the next step is the finite state machines, okay, which are again a tool to describe or to design the sequential circuits. Okay, you might have studied about this finite state machine method. Okay, and parallel to this you'll find that there are registers and ALUs in the structural domain which needs to be designed. Okay, and you'll find module placement in geometrical domain. Okay, a chip will consist of several modules. A module will consist of several cells. So within each of these things, you will have to bother about how to place different modules in a chip, how to place different cells within a module. Okay, so that's why placement is there everywhere. Okay, it's from geometrical point of view. Next comes as module description in behavioral domain. Okay, and contemporary to this is a leaf or a module or a logic block. Leaves, it's called a leaf cell in the structural domain. Okay, and then at this level we will be more bothered about cell placement, that how to place a cell within, how to place the cells within a module. Okay, and then as you move to the next step, you will find basically the Boolean equations at the bottom of it. Okay, you will find any kind of algorithm at the top level that will be converted into some kind of Boolean expressions as you move from top to bottom in the behavioral domain. Okay, and at this level you will have transistors in the structural domain, and the transistors are again manufactured with the help of mask or mask sets. Okay, so the masks are there, okay, which we will see what are masks. Actually mask is a glass sheet, I can say commonly, that will contain some pattern, geometrical pattern on this. Okay, so some areas are opaque, some areas are transparent like this. Yeah, so these are opaque areas, and this one are transparent areas. Okay, so when we bombard a light, okay, over this, the light will pass through this transparent area and will hit on the top of the silicon surface, and that surface is coated with light sensitive material, and then the process, then the things start. It will come in the fabrication process. We will see how the masks are used to fabricate the transistors. Okay. So basically, in each of these three domains, when we move from top to bottom, we move from the bigger thing to the smaller thing. And each of these domains have some parallels which can be related to each other. For example, at the processor level, we have chip floor plan in geometrical domain, and we have algorithm design in behavioral. What is the behavioral domain? Suppose again, as I said, that it tries to describe the behavior of the design in terms of if-else statements. Suppose when we do the coding, when you program something, you use if-else statements, right? What is that if-else statement? It's a kind of behavioral modeling. You try to describe something in terms of conditions. If this condition is met, this will happen. Else if second condition is met, second type of functioning should happen. Else if third condition is met, third type of functioning should happen. So in this way, the if else condition goes on. Okay. So that we will also see that in the lab, that how to do the behavioral modeling, how to do the structural modeling and data flow modeling in the VLSI lab. We will see those things. But right now, since this is the introduction part, so you may not be getting these things completely, but just try to keep these things in mind. Okay. So you can, so that you can relate it at that point of time when it comes in lab. Okay. Now look at here, the design hierarchy part. The design hierarchy, basically, it uses the concept of divide and conquer. Okay. If there is a complex design, it can be divided into simpler designs, simpler components. Again, that component can again be divided into more simpler components, and this division will go on until we reach at that level at which the management of the components are easy. Okay. So this technique involves dividing a modules into submodules and then repeating this operation on the submodules until the complexity of the smaller parts become manageable. Okay. So because it is very hard to design a complex system just by working at that level. So it is always wise and always beneficial to use this concept while designing, basically while designing any kind of circuit. Now look at this example. This is add 4, 4-bit adder. Okay, this is a 4-bit adder. Now this 4-bit adder is divided into 4 number of blocks. Each of block is having the capacity to add 1 bit. So this is a 1-bit adder, this is a 1-bit adder, this is 1-bit adder, this is 1-bit adder. Okay, so that they all of them combinedly perform 4-bit addition. Now again, we know that we can decompose 1-bit adder into the carry and sum part. Okay, this can be done for each of these adders. Okay, and we know the equations for carry and sum. We know what kind of gates would be used for designing sum and carry part, right? So for example, carry, it will be AND gate or gate. For sum, it will be XOR gates, uh, or gates, like that. Okay, now we can start at this level. Okay, we have different types of gates. We can use those gates to design the sum and carry part, and then design one adder. Once we design one adder, this block, okay, we need 4 such types of adder. So we can copy this adder 3 more times to get 4 number of 1-bit adder. Okay, You make 1 bit adder, you copy it 3 times, 3 more times, you get 4 number of adders. Why? Because the modules are same, so we can copy it and replicate it. Okay, and we combine these adders in a proper fashion, in a proper connection, to perform a functioning of 4-bit adder. Okay, so this becomes easy. This becomes easier, right? Okay, and you try to use this concept whenever you design a complex circuit, wherever it may be a circuit related to communication, circuit related to some kind of DSP application, some kind of filter, some kind of basically any kind of circuit. If you are designing some kind of Arduino based design, whatever design, if it's a complex one, you can use this concept wherever it is applicable. Okay, it will always give you some beneficial result. So this is the structural decomposition of a 4-bit adder showing the levels of hierarchy. Okay, now this is again example that shows a 16-bit adder decomposed into 4 number of 4-bit adders. Okay, and we had just seen that how to decompose a 4-bit adder. Okay, like this. So we have one 4-bit block. We can replicate it 3 more times, and we can combine all these 4 blocks to get a 16-bit adder. Okay, so this is simple, right? Okay, now this shows the uh, geometrical decomposition, the same 4-bit adder. Okay, now this is shown in terms of diagram. That's why it's the geometrical decomposition. Look at here. So it shows that this is a 1-bit adder, 1-bit adder. This is a 1-bit adder. This is a 1-bit adder. This is a 1-bit adder. Okay, so 1 1 1 1 total. This total block forms 4-bit addition, and this is 1 bit. This individual blocks are 1 bit. Okay, now for this lowest block, we know that we should have some input and outputs. Okay, it's having this A0 input, B0 input, and CI the carry input, and it is producing the sum output and the carry out output. Okay, now we know that the carry out of this first stage should enter into the carry in of second stage. So that's why it is given here. It is again having some inputs, some output, and some carry out. The carry out of second stage will go enter into the carry in of third stage. So likewise, it is connected here like this. So each of blocks is are having its own inputs, okay, and its own output. Okay, and since this is a geometrical domain representation, it will have certain coordinates with its hundred unit in length. So this becomes a 100 coordinate. This point. This becomes a 200 comma 200 coordinate point. This point becomes 100 comma 300, and this becomes 100 comma 400. Okay, so total length is 400 units, and one block length is 100 unit. Okay, now in this block they have shown the location of each of these pins also. For example, the pin location of this carry input is 50 comma 0. The pin location of A input pin is 0 comma 25. For B it is 0 comma 75. For carry out it is 50 comma 100. For S it is 100 comma 50, and this is 100 comma 100. This is with respect to one single block. Okay, and this 100 comma 400 is 400 is coming here by taking all these geometries in consideration. So basically, this one complete block, which is a 4-bit adder, can be decomposed into four number of blocks, each of which is of 1 bit adder, and they can be connected geometrically in this fashion to work as a 4-bit adder. Okay. So in the physical domain, in this is the geometrical domain. In the physical domain that we had seen just before this, partitioning a complex system into its various functional blocks will provide a valuable guide for the actual realization of these blocks on the chip. So it actually provides a great amount of information, because we get to know that okay, this particular block is consisting of these many sub blocks and like that. So we get to know the detail behind those things. Okay. And this physical view describes the external geometry of the adder, the locations of input and output pins, okay, and the pin locations that allow some signals to be transferred from one sub block to the other without external routing. In this case, the carry signals. Since we know that the carry output of this block is going into the carry in of this block, so we can directly connect these two carries at a single pin location without the use of any external wire or routing. So in this sense, it saves on the cost of wiring, extra wiring or routing that had to be done. Okay. So this is the geometrical domain representation, and just look at here. Last, this is the hierarchy of 16-bit Manchester adder. And this is the actual layout which will be sent for fabrication. Okay, so this is the actual thing. Okay, this will be sent for the fabrication in the foundry in the company. Okay, so this is a 4-bit block, this is a 4-bit block, and this will be a 4-bit block, and this will be a 4-bit block. So total it will be a 16-bit adder. And when you look carefully inside this 4-bit, you'll find this is 1111. So this is 1-bit block. Okay, this is 1-bit block. Like that we have these four number of 1-bit blocks. And when you look into the structural, the layout, you'll find some patterns occurring, and each of these patterns corresponds to some adder. Okay, this is just for reference. Okay, do not have to draw this, but just for this is the layout which will look like this for any circuit. And by looking at a layout, we can find some patterns. Okay, and we can guess those things, that okay, this bigger layout consisting of smaller layers, smaller layouts, and that smaller block is consisting of some, even some smaller blocks, like that. Okay, so I stop here, and then I will resume here in the next class. Okay, if you have any doubt, you can ask me, students, or you can, else you can give your attendance in the chat box. Write your roll number and name in the chat box for attendance, and any doubts are welcome. Write your roll number and name in the chat box for attendance, and you can ask your doubts.
Sir, can you please share the PPT in the group?
Okay, I will share it, don't worry. I will share the PPT. Okay,
Thank you,
and
sir.
I will also share the recordings of the lecture. Okay.
Thank you, sir.
I have, yeah, I had